If a black hole is a sphere, why do we call it a black hole? Well, you could say it's because anything that falls in never comes back out, so it's like a bottomless pit. But then, where does all that stuff actually go? Does it end up inside the black hole? Or is it forever frozen at the event horizon? To answer that, we first need to figure out another question. What's inside a black hole? Black holes have two weird features: the gravitational singularity and the event horizon. Early on, scientists noticed that in Schwarzschild solution, things go haywire at the center of the black hole, and at the Schwarzschild radius, basically, infinity shows up. And infinity is supposed to be a math thing, not something that happens in real physics. Whenever infinity pops up in calculations, it usually means something's wrong with the theory. So back then, Schwarzschild solution only described what happens outside the event horizon. What was inside, nobody knew. But infinity isn't always unsolvable. Sometimes, with the right math tricks like renormalization or switching coordinate systems, you can make it disappear. For example, when scientists switched from Schwarzschild coordinates to Kruskal-Szekeres coordinates, the infinity problem at the event horizon vanished. Finally, we had a basic understanding of black hole structure. When a massive star runs out of fuel, it collapses inward nonstop. And by nonstop, I mean nothing can stop it. Not electron degeneracy pressure, not neutron degeneracy pressure, nothing. The collapse just keeps going, crushing all that matter into a single point, the singularity at the center of the black hole. So, according to classical general relativity, the inside of a black hole is just empty space except for that one infinitely dense point. But that can't be right. Why? Because even though we fix the event horizon problem, the singularity is still there. In general relativity, spacetime is smooth and continuous, so the singularity has zero size, zero volume, meaning infinite density. We patched up the event horizon with coordinate changes, but the singularity's infinity problem still unsolved. That's one reason why some think general relativity is incomplete. So what's the fix? When in doubt, bring in quantum mechanics. If gravity alone can't solve it, mix in some quantum theory. In 2001, scientists applied condensed matter concepts to gravity and found a new solution to Einstein's equations, a strange object very much like a black hole, but with no singularity and no event horizon. Instead, it's a hollow sphere wrapped in an ultra-thin, super-dense shell, filled with a special kind of vacuum. This isn't normal empty space, it's a de Sitter vacuum, packed with crazy energy, expanding outward in all directions. But that expansion gets stopped by the shell, which is thinner than an atomic nucleus, yet incredibly dense. The shell is made of the star's leftover matter, the stuff that would have become a black hole. The researchers call this object a gravistar, or gravitational vacuum star. From the start, gravastars were seen as an alternative to black holes. By adding quantum effects, they not only got our idea of the singularity and event horizon, but also solved the black hole information paradox. So how does a gravistar form? Like a black hole, it starts with a massive star collapsing. But instead of squeezing forever, the matter stops at a certain point, triggering a phase transition in the core, turning it into a de Sitter vacuum. This vacuum bubble expands violently, pushing outward against the collapsing star's remains. The inward pull of gravity and the outward push of the vacuum reach a balance at the Schwarzschild radius, forming that dense shell. The shell and the vacuum inside, that's the gravistar. Gravastars share a lot with black holes. Their size matches a black hole S, with the shell sitting right around the Schwarzschild radius, like an event horizon. They're just as massive, just as gravitationally powerful, bending light the same way. They even have extreme gravitational redshift, light getting redder and dimmer as it nears the shell, just like near a black hole's event horizon. But unlike black holes, gravastars don't have infinite redshift because their shells have actual thickness. They're also pitch black, near absolute zero, and hard to detect via thermal radiation, just like black holes. The difference? Their temperature might not be as evenly spread. Gravastars also pull in matter and form accretion disks. But instead of crossing an event horizon, the matter piles onto the shell. For black holes, matter supposedly falls through the horizon, reaching the singularity, but only if you're the one falling. To an outside observer, it just freezes at the horizon, fading from view. Wait, how can it both cross and freeze? Simple. The light from the falling object takes forever to escape, so you never see it actually enter. That's why it's called an event horizon, the boundary beyond which events become invisible. This highlights a key difference. Black holes are warp spacetime, not physical objects. Gravastars, on the other hand, are made of matter, which might make them easier to accept. But gravastars aren't perfect. While they clean up the outside, the shell and its vacuum core bring new puzzles. Black holes are simple, no hair, just mass, spin, and charge. Gravastars, their shells are made of something.